In modern AI engineering, the most common way to build an agent is wiring a large language model into a rigid sequence of code. While these systems appear independent, they are locked into a fixed path determined by the programmer. This approach has fueled a surge of tools marketed as AI co-scientists and coding assistants. These products are designed to automate complex, multi-step tasks, promising a significant increase in engineering output. However, when we look under the hood, the intelligence of these systems often resides within the human-engineered workflow rather than the model itself. Consider a standard coding agent pipeline. The large language model acts as a processing node, distinct from the logic determining its use. Decisions to retrieve memory, iterate loops, or call tools are orchestrated externally. The model doesn't decide to try again, it's told to by a human's code. Because their competence depends on this external scaffolding, these systems are agentic tools. They perform tasks with high efficiency, but they lack the internal architecture required for independent agency. This distinction echoes René Descartes' view that true agency requires the capacity for independent thought. Action must be a result of internal reasoning, not just a mechanical response to an outside force. To apply this to modern AI, we have to identify the technical boundary where mechanical automation ends and true machine autonomy begins. For a system to be truly agentive, the structures that drive its behavior must be endogenous, meaning they arise from within the system's own architecture. This requires evaluating a system across 5 dimensions: goals, identity, decision-making, self-regulation, and learning. Most current systems hard-code these dimensions through external prompts. An agentive system must possess the capability to generate these structures internally. Chaining LLM prompts together cannot bridge this gap. But crossing into genuine autonomy requires a fundamental shift in how we architect AI systems from the ground up. Researchers have proposed the Goal Identity Configurator, or GIC, architecture as a blueprint for an agentive model. The first dimension is hierarchical goal decomposition, breaking an abstract objective into executable subgoals. These are passed to an internal decision-making node, removing the need for external Python scripts. The decision-making node independently evaluates the subgoals and initiates the necessary actions to complete them. In this model, the system is no longer waiting for a human-engineered loop to trigger its next operation. Internalizing the goal-setting structure provides the mechanism for a system to initiate action on its own terms, rather than simply reacting to instructions. Action alone is not enough. In environments with dynamic shifts and unpredictable obstacles, a trial-and-error system will encounter situations its programmers didn't anticipate. The GIC architecture solves this through simulative reasoning, which is powered by an internal world model. This world model is a separately trained component, isolated from the primary language model. This separation allows the agent to simulate different actions and predict how the environment will respond before it ever executes code in the real world.
This is similar to human cognition. We can visualize the results of a physical action before we commit to it. By utilizing this internal world model, the system can navigate edge cases and novel environments without needing a human to provide a rule for every possibility. The system also maintains an internal identity, governing how the agent adapts its parameters. This identity node manages resource allocation. If the state requires higher efficiency, it adjusts internal data throughput accordingly. This creates a form of learned self-regulation, adjusting strategy upon detecting failure. Finally, all these experiences are captured by a self-directed learning loop. The agent pulls data from 2 sources: its successes and failures in the real world, and the results of its internal simulations. This dual learning approach helps the system improve its performance in new environments much faster than a standard model. Internalizing identity, regulation, and learning creates a cognitive loop that maintains system stability even when predefined workflows are no longer applicable. Once these components are in place, we have the fully constructed GIC architecture. When we provide complex input, we see the entire endogenous lifecycle, from goal generation and simulative reasoning to execution and learning. At no point does the data need to exit the system to be processed by human-engineered glue code. This internal cognitive cycle is what allows a system to operate successfully in the open world, rather than being limited to a narrow, controlled environment. Addressing concerns. Removing human scaffolding and granting systems internal autonomy often leads to questions about safety. The fear is that we are building uncontrollable systems. This is a common theme in science fiction, where machine agency inevitably turns destructive once it is no longer tethered to human instruction. But in the real world, systems that rely entirely on external scripts are often brittle. Because they only follow predicted steps, they cannot adapt to a new situation. When the environment changes, the rigid script fails. The shift toward an agentive GIC model provides a system capable of self-correcting autonomy, rather than one that relies on a human programmer to predict every outcome. To build systems that are safe in an unpredictable world, we are trading rigid external constraints for fluid internal self-regulation. This shift also introduces a new way for humans to maintain oversight of autonomous systems. Because the GIC's distinct internal structures are highly auditable, we can observe goal hierarchies and world model simulations. Human operators interact directly with these nodes, injecting constraints or adjusting regulation parameters without shutting down the agent's autonomy.
This is much more precise than trying to debug a chain of prompts, as it allows us to see exactly how the system is reasoning through its objectives. Machine agency is not something that happens by accident when a model becomes large enough. It is a matter of deliberate architectural design. If we intend to build safe, capable AI, the engineering community must move past simulating agency with Python scripts and begin architecting endogenous cognitive structures.